SwayamPrabha. Digital India. Educated India.
Good morning. In the last class we had seen what is the head required and what is the kind of flow rate that goes through the pumps in a pump fed system. In this class let us look at what are the efficiencies that are possible with these pumps and how does it affect the overall performance of the rocket engine and some other related issues. Now from pump theory it is a theory wherein you non-dimensionalize the head, right, and it is a function of rotational speed and impeller diameter. So it is written like this: delta P by this is the non-dimensional head, okay. This is equal to a function of okay. So this is non-dimensional rotational speed, and this is non-dimensional impeller diameter. Now if you see here, this comes from Buckingham pi theorem, which you must have studied sometime in your undergraduation. The rho p here corresponds to the density of the fluid, omega corresponds to the rotational speed in rpm, and dp corresponds to the diameter of the impeller, okay, and q dot is the flow rate and delta h is the actual head rise, okay. G is acceleration due to gravity. Now if you have this, then you can plot it as shown here in this figure. On the x axis you have the non-dimensional rotational speed given as nsp, and on the y axis you have the non-dimensional impeller diameter given as dsp. If you notice here, the numbers that are given here are efficiencies 0.6, 0.7, and it goes all the way up to 0.9, right. Now if you want to have, as seen here, if you want to have high efficiencies, you need to be in this region, right, which means that your impeller diameter needs to be very small, and also your rotational speeds needs to be very large. Okay. So this is NSP, and this is DSP. So for high efficiency, NSP needs to be large and DSP needs to be as low as possible. So then you will get to very high efficiency. Why is high efficiency required? If you remember, the efficiency of the pump matters a great deal, simply because that determines how much of propellant you are going to consume to pressurize the fluid. Okay. So if it is as small as possible, then the rest of it can be used for useful propulsion activity, right. This does not directly come into propulsion activity, because the flow through the nozzle is what causes the propulsion effect. So in that sense, you would want to minimize this to as small number as possible, but actually speaking, how much is it possible to reduce it to is given in this table here. If you look at the power of the pump and the efficiencies, the actual achieved efficiency is somewhere around 44%, and it goes up to something like 60% for the pumps, whereas for the turbine it goes all the way up to 80%. Okay. So which means that even though you spend a lot of propellants for turning the turbine, all of it is not obtained as useful work to run the pump. Okay. Only a fraction of it is. If you look at this table here, it gives you what are the RPMs that these pumps are run at. Remember, we said that the diameters need to be small and rotational speed needs to be as large as possible. If DSP and needs to be small and NSP needs to be large, NSP invariably means, if you look at this, this is NSP for a fixed flow rate and pressure head. Okay. For a fixed flow rate and pressure head, the only way you can get a high NSP is by increasing the rotational speed. And if you look at the numbers here, they are rotated at very high speeds for the LOX hydrogen systems, something in the range of 40,000 RPM. Okay, very high RPMs. What does this cause any problem is what we need to look at. There is something called cavitation in pumps, okay, which comes out as a result of this high RPM. Now, what usually happens is, if you remember, LOX, liquid oxygen and liquid hydrogen are low boiling point fluids, right. You must have done this experiment somewhere wherein you have a tank and you tend to suck through the tank. It's something like this, that let's say you have a tank here and you have a pipeline that is going here. If you look at the actual difference in head, it is this much, right, but there is a limit because at this point you don't want the pressures to drop below what? Vapor pressures, right. So similarly in pumps, what happens is when you rotate it at very high RPM, right, the static pressure can go below the vapor pressure at that temperature. Okay. Once that happens, then bubbles get formed, right. It boils in some sense and bubbles get formed. These bubbles, they move over to a high pressure area and then implode, right. When they implode, they cause severe vibrational loads. Okay. And that is not the only thing, the mass flow rate through the pump kind of oscillates. Okay. Now only the vibrational aspect is not such a serious problem in a launch vehicle, simply because we are looking at a one time use, right. We are not looking at using it very often, and unless you are looking at space shuttle main engine and things like that, you are not looking at using it very often. So you could probably deal with the vibrational part, but the other part that is of very great significance is the fluctuations in mass flow rate that it leads to. Okay. How does this affect the functioning of the rocket motor? Firstly, the mass flow rate that is coming in is fluctuating, right, which could trigger an instability in the liquid rocket motor, and it could have very, very serious consequences on the mission itself, because of instability. Usually liquid rocket motors are very, very prone to combustion instability, and usually they have very, very high frequency instability, which simply means that as we had discussed earlier with regards to solid propellant, you are having a fatigue loading of the motor, right. And if the frequencies are very large, firstly they are being subject to very high heat transfer rates and also very high stresses. And remember, the factor of safety that we can use is very small, and therefore it could lead to a catastrophic failure of the whole setup. So you wouldn't want that to happen. So therefore it is pretty much essential to ensure that cavitation in pumps does not happen. Okay. So it is imperative that we reduce or we eliminate the cavitation in pumps. One easy way to do this is, in some sense, if you look at it, if you kind of increase the pressure here, right, if you increase the pressure here, then you will not get this problem here, right. Or in other words, what we are looking at is increasing the pressure in the cylinder itself or the storage tank. One way to overcome this is but what does that mean? If you remember, this is a turbo pump fed system. We said the pressure in the tank is something of the order of 3 to 6 bar, which will ensure that the wall thickness of the tanks is very small, right. But if you increase the pressure, then your wall thickness goes up and your weight goes up, which is not a desirable solution here, right. So there are other ways to tackle this problem other than increasing the pressure in the tank. So this increases there is something that we can define as known as net positive section head. that is P stagnation minus P vapor pressure if we increase this part, which is what is in tank, which is what we discussed right now. Okay. The other way to look at it is something that has been quite widely used is to use something known as an inducer. Okay. Inducer or separate pumps in series. So, the way pumps operate is like this. In the there is a rotor and a stator, right. In the rotor you rotate it at very high RPMs and therefore you give it the kinetic energy, or in other words the velocities are very high, which is kind of recovered in the diffuser stage, right, or the stator stage as pressure. Fine. So, if you are giving a very high rotational speed in the first stage itself, then it gives rise to this kind of problems. But later on, if you in the other stages after the first stage, if you give it, this problem is not very severe, but this is very severe in the first stage. Okay. One way to overcome this is to have things in series. That is, you do not look to give the entire pressure rise in only one single stage, but give it in a number of stages, okay, which is what is having separate pumps in series means. Okay. The other way is to use an inducer. Now, inducer is also a pump, but the only difference here is inducer, the delta H that is imported you tend to impart a very low head in the first stage or the inducer stage. Okay. In a sense, you are rotating at the same RPM, all of it is mounted on the same shaft, but the head rise that is given is very small in the inducer, so that the pressure at the exit of the inducer is higher than what causes this problem of cavitation. Okay. Then you can give it the head rise in the other stages, right. So, in this way you are going to overcome this problem. This is in a sense the same thing as having pumps in series, but in this case an inducer is some kind of special pump wherein a very small head rise is given, although it is rotating at the same RPM. Okay. The velocity triangles are adjusted such that the head rise given is very small. So, in this way you can overcome this problem of cavitation in pumps. Now, there are various ways in which one could arrange the pumps and the turbines, which is shown here in this figure here. Okay. If you look at this figure, the first arrangement as shown here is one in which the pumps are arranged back to back. that is, one is the fuel pump, the other is the oxidizer pump, and they are mounted on a common shaft that connects to the turbine. Now if you look at this kind of arrangement, what it does is it reduces the axial thrust, right, because the axial load on this pump is in one direction, the other pump is in the other direction. This kind of cancels each other out, and you have to deal with a smaller problem of axial loads, the axial thrust that comes on the shaft. Okay, the bearing that needs to take this can be designed such that it deals with a smaller axial thrust. This is in some sense probably similar to what some of you have studied in IC engines, the problem of balancing, right. If a piston is moving inside a cylinder, then if it is not properly balanced, right, if you have an arrangement wherein it is two cylinders are opposed, then the imbalance in the loads get cancelled out, right. Or if you have an arrangement, radial arrangement of cylinders, then there is no problem of balancing. But if you have only one cylinder, there is a problem with balancing, right. So that is very similar to the problem that you have here. So this takes care of in some sense the axial thrust. There are other arrangements that is used, that is this is known as some pancake arrangement. Now in this arrangement there is a turbine between the pumps. The turbine and the pumps are run at different RPM and they are connected through a gear train. Okay. In the first one there is no gear train connecting the pumps and the turbines. So whatever RPM the turbine is running at, the same RPM is where is the RPM that the pumps are run at. Here you have an extra control on the RPM of the pumps. Okay. Then you have various arrangements wherein you have a separate turbine for each pump in this case. So if you look at this C, B and F here, you can use this when there is a difference in the density of the two propellants. Like if you have LOX and LH2, LOX has a density of the order of 1100, right, and the density of hydrogen is very low, something around 70. So they need to be run at different RPMs, right. If you have to run it at different RPMs, either they have to be connected through a gear train, right, or they have to have separate turbines which are running at different RPMs, fine. In this way you can ensure that these arrangements, that is B, C and F, take care of things which have dissimilar densities. Okay. Now the arrangement shown here, D, which is the turbine and the pumps are, in this case the turbine was on one side and the pumps were on one side. In this case the turbine is in between the two pumps. This works fine for propellants with similar densities, okay, because the head rise required is nearly the same. So therefore if the densities are the same, you can work it out that they need to be rotated at the same RPM. So this works for propellants with similar densities, whereas B, C and F work well for propellants with dissimilar densities. Then this arrangement C and G, you have in this case in C the pumps are arranged in series, whereas in the other one you could have turbines are arranged in series, that is the gases pass through the first turbine and then the same gases pass through the second turbine. So depending on what is the head rise that is required in the two pumps, you can work it out in this fashion. But whereas in this case the turbines are in parallel, okay, that is the flow coming in from the gas generator is fed to both the turbines, okay. This kind of arrangement has been used in space shuttle main engine, and this kind of arrangement was used in F1 engine, okay, the F1 engine on Saturn IV that took man to moon had this kind of arrangement for LOX kerosene, okay, wherein densities are similar. That is, if you look at LOX, it is around liquid oxygen is around 1100, the other one is around 800, okay. So this finishes our discussions on the pressure fed systems, that is not the pressure fed, the turbine turbo pump fed systems. We had earlier discussed how to design a pressure fed system. So we have discussed the various kind of feed systems that are possible. Now we have discussed what happens in the nozzle earlier, we have discussed the feed systems. Let us now discuss what happens in the thrust chamber, okay, thrust chamber of a liquid engine. The first thing that one encounters in the thrust chamber is what is known as injector. Now, why do we need a injector? Why not inject, you know, we are injecting in some case two fluids if it is a bipropellant system, and in a monopropellant system we are injecting one fluid. Why can't we simply inject them as one single pipe flow, right? Why do we need these kind of small injectors? Are these kind of if you look at the liquid rocket motor, there will be this kind of large number of small holes this will be the kind of arrangement in a liquid rocket motor, and let us say this is the thrust chamber, and here you have the nozzle. Now if you look at it from that direction, this is the kind of arrangement that you will have. The liquids are pumped at high pressure through these large number of holes. Now the question is, why do we need this kind of injectors. Okay. The answer lies in the fact that if you are looking to have a reaction, right, you want these fluids to firstly vaporize, right, and then react. Reactions take place in the gas phase. So there are a few things that are happening in the thrust chamber. First is what is known as automation. Okay. So you have atomization, then you have okay, these are the processes that need to take place within a liquid rocket motor, and all these need to be completed before it enters the nozzle. Okay, all the reactions need to be completed. If this happens, there is something known as combustion efficiency that we look at, wherein how much of this is completed before it enters the nozzle. It is good to have a larger fraction of these reactions, something in the range of 92 to 95%, because then what you will get is, from the ISPs that we had calculated, we will be able to get a fraction of those ISPs depending on the value of combustion efficiency. Okay. The heat release that we get depends on what is the combustion efficiency. If reactions take place after this, then we will not be able to utilize it that effectively. So you need to have all the reactions or a large fraction of it getting completed before it enters the nozzle. Now if you look at it, there are three processes that take place. This is like a relay race, right? First this happens, then this happens, then this happens, right? So in a relay race, who gets to decide how fast the relay race is completed, right? Does the fastest one get to decide how quickly the race gets over, or does the slowest one? The slowest one is the limiting factor, right? So the slowest one gets to decide what kind of times it takes to complete the reactions. So typically what happens is, these liquid droplets are coming in. Okay, one can define something known as a residence time. Okay, residence time is nothing but what is the time that is available for reactions to be completed. Okay, or what is the stay time of this fluids in the combustion chamber. Okay, so we have something known as residence time. So all these processes need to be completed within this residence time, or a large fraction of this needs to be completed within this residence time, so that the combustion efficiency is high. Now typically the stay time or the residence time is of the order of 3 to 5 milliseconds. Okay. Remember, in a liquid rocket motor, unlike in a solid rocket motor, you are storing the propellants also in the same chamber, right? In liquids you are able to store them separately and you introduce them in a chamber where they combust and react. So the combustion chamber is very, very small, Okay. So the residence time therefore is very small in a liquid rocket motor. Now let us look at what are the typical times for these three events to happen. The vaporization time of droplets is a strong function of the size of the droplet. Okay. So it goes as something like d naught square by d1, and for 50 micron, 100 micron and 150 micron droplet size, the time for vaporization is something like 1.8 millisecond okay. So if you notice here, if the droplet diameter is small, then the vaporization time is small. If the droplet diameter is large, then the vaporization time is very large, and therefore if you have a stay time, residence time of this, then most of the reactions won't get completed. The reaction times are much smaller it is of the order of 0.5 to 0.05 milliseconds. So it is very much smaller compared to this. So this is the slowest process in all this. Okay. So therefore this is the one that decides how fast the reactions get completed, right. So depending on the length of the chamber, you can estimate a residence time, and all your reactions need to be completed within that. The reason why the reaction times are very small is if you recall what we had said about reaction rates, right. If you look at the relationship for reaction rate W dot triple dash that we had derived earlier, it was something like right into YF YO. So if you notice that it's a strong function of pressure and temperature, right. The temperatures inside rocket motor are very high, something of the order of 3000. So this term will be large, and also if you remember, liquid rocket motor, depending on the kind of pressurization systems that we have, if one is looking at a pressure fed system, the pressures are very low, something of the order of 30 to 40 bar, right. But if we are looking at the turbo pump fed systems, then the pressures are extremely high, something of the order of 200 bar, 100 to 200 bar, and the factor to which it is raised depends, it goes something like it's of the order of 2, it's square of the pressure. So the pressures are very high, then the reaction rates are very large, and therefore the reaction time is very small. So in a sense this reaction time is small primarily due to the coupled effect of pressure being large and temperatures being large. Now it becomes clear why we need to do this atomization, right. Atomization is the process in which you create these small droplets. Okay. If you create these small droplets, then the vaporization time, as we see here, goes as something like d square. We will be discussing what is that factor or a little more in detail of this vaporization time. So the smaller the droplet, the faster it evaporates. This is something similar to, a matchstick is made very small, right, simply because if you look at the surface area to volume, which is very, very important, right, in heat transfer, the larger the surface area to volume that you have, the better it is for heat transfer. So in a sense, if you are creating very small droplets, the surface area to volume increases, okay, and that means there is a lot more heat transfer that is taking place instead of having one large droplet. Okay, if you break it up into very, very fine large number of droplets, then the surface area to volume is very large and heat transfer is better, and therefore its vaporization times will be much smaller, as is seen here. So you need to kind of make sure that it is atomized, that is, it is broken into very fine droplets, and then these fine droplets will then evaporate fast and the reactions take place in the gas phase, and these get completed very, very quickly. Okay. Now the vaporization time TV is given as where BV, if you recollect, is the transfer number that we had discussed earlier, that is, it is the ratio of here TB indicates the boiling point. Okay, TB is the boiling temperature and L is the latent heat in a sense. We are making an assumption that all the liquid is at its boiling point, right, and then it is only required to be given its latent heat of vaporization. If you have the liquid, if the boiling point of the liquid is very high, this is a fairly good assumption if the boiling point of the liquid is very low, something like LOX and hydrogen. But if the boiling point of the liquid is very high, then you need to add the other term, that is the heat that is required to take it from whatever temperature the liquid is at to the boiling point. Okay. So this is Kg is nothing but the thermal conductivity, this is the specific heat, then this is the density of the liquid. What you can see here is that the vaporization time is a very strong function of the diameter of the droplet. Okay. So this is known as something, this is called as the d square law. Okay. So you could rewrite this as something like okay. So this is nothing but a constant that takes into account all the other things other than the diameter. Okay. So as we can see here, the vaporization time is a strong function of the diameter, and therefore it makes sense to have very small diameters. Okay. Now we will discuss in the next class how we can get the small diameters by the process of atomization. What is the process of atomization and how does it ensure that you get very small diameters of droplets, and what are the various arrangements that are possible. Okay. If you remember, most of the propellant combinations, you have two liquids. It's only in the case of liquid hydrogen and liquid oxygen, wherein if you use hydrogen for the regenerative cooling part, it is mostly a gas while coming into the combustion chamber, right. So we will discuss what kind of arrangements of injectors we need to have for various kinds of propellants in the next class. Thank you.